In the Leetcode problem, toSum, we're given an array of integers nums and an integer called target. We want to return the indices of two pairs of numbers that, when summed together, add up to the target. For example, given a list of numbers 2, 7, 11, and 15, and a target of 9. Can we see two numbers that add to 9? Well, 2 and 7 can be summed to add up to 9. The problem tells us we need to return the indices of these numbers. So we return a list containing 0 and 1, which is the index of 2 and the index of 7, respectively. They also tell us that we can assume the input has exactly one solution and we may not use the same element twice. For example, we're given an array containing 3 and 3 and a target of 6. Even though we could return either 0 and 0 or 1 and 1, both of which are the indices of pairs of numbers that sum to target. Because we'd be returning the same element twice, it isn't a valid solution. We must return 0 and 1, although they tell us we can return results in any order, so 1 and 0 would also be acceptable. In this video, we're going to solve the problem using Python 3. If you haven't already, make sure you pause the video now and try it yourself. You'll get more out of these solutions if you have already attempted the problem. Let's start with the most direct approach, brute force. Here we'll sum every two pairs of numbers until we find the sum that equals the target. For example, let's say nums is an array containing 4 elements, 3, 5, 10, and 9. And we're given a target of 15. We can simply sum every two pairs of numbers until we find the pair that sums to equal the target. Then we return the indices of these numbers. Let's code that up. In the header file Leetcode provides, we can see that nums is supplied as a list of integers, and we're expected to output a list of integers. It is common practice to represent arrays as lists in Python, although Python also has an array type. Firstly, we'll use a for loop to iterate through each value in nums. However, since we need to return the indices of the pairs we find, we can utilize the enumerate function, which gives us the position and value for every item in the list. Now, we can add another inner for loop through nums for each step of the outer loop. In this inner loop, we must ensure we don't compare the same values to the outer loop. Finally, we check the result of the sum of the inner loop value and the outer loop value. When we find our match, we return the indices of each position. Now, let's talk about the performance of this algorithm. Suppose we define a variable n as the length of the nums array. Our first pass through nums requires n steps, but for every element of the nums array, we need to do another full pass, n steps. So we will need n times n steps to complete our algorithm, or n squared steps. In other words, the algorithm operates in a time complexity of big O of n squared. Let's submit that and see how we go. That's not great. We're at the bottom 5% for runtime speed compared with other Leetcode solutions. Let's see if we can optimize that. Notice how in the brute force example, we summed 3 and 5 in the first pass, and then in the second, we summed 5 and 3. Obviously, these two pairs give the same answer in any order. Since order is not important to our results, after we have checked 3 against every other number, we no longer need to sum any number with 3 again. So when we do the second pass, we should start from 1 above the current position. Let's see a complete example. Here, we've compared the first value to 5 to every other number. In the second pass, we don't need to sum any number with 5 again. And the same for the 10 until we found our answer. We are still comparing all pairs together, but distinct pairs are only compared once. Let's go ahead and make that change to the code. Now, in the inner loop, instead of iterating through the entire nums array, we start from position I plus 1. I'm using the slice notation in Python, which allows us to retrieve a subset of a list, and I'm also passing I plus 1 as the start argument to enumerate to tell it which number to start j from. We no longer need the comparison to check for the same element since the inner loop is always one step ahead of the outer loop. Let's submit that and see if our speed improves. Indeed it does. We went from the bottom 5% to the bottom 18%, but there is still plenty of room for improvement. Let's take a look at the time complexity of this algorithm. For the first iteration of the outer loop, the inner loop needs n minus 1 steps. For the second iteration of the outer loop, the inner loop needs n minus 2 steps, and so on, until finally, in the last iteration, the inner loop has no steps at all. The sum of these numbers is called an arithmetic series. We can simplify this to n times n minus 1 over 2, or just n squared minus n over 2. In big O notation, we're only interested in the highest order terms, so we can simplify this again to just big O of n squared. So, although our algorithm has improved in real-world speed, the underlying time complexity has not changed. Let's try a different approach. The two-pointer technique is an efficient method for finding pairs of values in a sorted array. We start with a pointer to the start of the list I and a pointer to the end j, and we increment I or decrement j until we find a solution. However, there's one caveat to this approach. The input list must first be sorted. Since Leetcode does not provide us with a sorted list, we'll need to sort it first. That means the algorithm's runtime performance will incur the cost of sorting the array. Also, since we need to return the indices of the pairs, we'll need to keep track of the original positions as they will otherwise be lost when sorting. Now, we assign ourselves a pointer I at the start of the list and another j at the end. Given a target of 14, we sum the value at I with the value at j for each iteration. Here, since the result is lower than the total, we increment I. Now the value is too high, so we decrement j. We keep doing this until we find our answer. Let's code that up. Firstly, we need to keep track of the original index values. We can use enumerate to convert a sequence of values into a sequence of index value tuples. Then immediately convert that iterable sequence back into a list. Then we sort this list. The sorted function accepts a key argument, which is a function used to fetch the value to sort with. Here we're extracting the value at position 1 of the tuple. Now that we have a sorted list, we can apply the two-pointers algorithm. Firstly, we initialize I to 0 and j to the last position in the nums array. Now, while I is less than j, we sum the value at position y and the value at position j. If the sum equals the total, then we have our answer. We can fetch the original positions from the first element of each tuple and return them. Otherwise, if the result is too low, we increment I, or if the result is too high, we decrement j. Let's submit that and see how we go. Much better. Now we're in the top 20% of submissions. Let's talk about the time complexity of this approach. The two-pointer approach is typically in big O of n, since we move I or j every step, so we will only need n steps, at most, to find our values. However, since we first needed to sort the list, we must add that to our total time complexity. Sorting in Python has a runtime of big O of n log n. We'll also need one more pass to store the original index position, which adds another n steps to our runtime. Now, in big O notation, we're only concerned with the highest order terms, so we can simplify the runtime to just big O of n log n. That's a lot better than n squared, but let's see if we can do it in one pass. For the one pass solution, we need to rethink the problem a bit. Notice how in each step we're summing x and y, which adds to the target. But we can rewrite the expression as y equals target minus x. This allows us to rethink the problem. As we walk through the list, we can subtract the current value from the target. Then we can check if the result is in nums. However, checking for a value in an array requires n steps. How can we do this check in constant time? Well, what if we created a hash table to cache each value as we iterate through it? Since a hash table has a constant time lookup operation, we only need one step for each element of nums. If we populated the hash table as we walked through nums, storing the value as the key, and the position in the array as the value. Since adding to a hash table also operates in constant time, we only need one pass for the whole algorithm. Eventually, we will subtract a value from the target and find the result is already cached in the hash table. We can then look up the entry's value to fetch the index and return it alongside the index of the current number. Let's code that up. Firstly, we'll create the hash table called scene. Hash tables can be represented in Python using dictionaries. Now we enumerate through nums again. This time, we subtract the current value from the target and check if it's in the hash table. If it is, we fetch the index from the hash table and return it alongside our current index. Otherwise, we add the current value to the hash table and continue our loop. Let's submit that and see how we go. Great. Now we're in the top 15% of solutions. Let's talk complexity of this algorithm. Since we can look up and add to a hash table in constant time, all the operations that happen at each step of the for loop are in constant time. Since, in time complexity analysis, we are only interested in the highest order terms, we have a time complexity of big O of n, where n is the steps required to pass through the list once. However, it's worth noting that we now need to store every element of nums in our scene hash table, which increases our space requirements. In the worst case scenario, we will need to store another copy of every element of n in the scene hash table. So we also have a space complexity of n. And that's it. Thanks for watching. Please let me know in the comments how you went solving this problem. Also, subscribe for more straight to the point coding and technology videos like this.